lectures or the lecture. What I'd like to do today is I'd like to go over both sections 6 and 7. So the same idea. What we call hierarchical models. The book doesn't call it hierarchical models. That's a term that is now commonly used. So let me go ahead and bring up the text. I'm probably going to need to give you a context of how this works, and so I'll bring up part of the book. We're going to be talking about what is called a split plot design, and that is sort of combines a completely randomized design with repeated measures. And so what you're going to have is whole plots, which are going to be organized into a completely randomized design, or block design. But again, as I said, you're going to have sort of subsampling or repeated measures. So I think if I show you an example in the book, it will be easiest to see this. Not sure the best place. Hopefully we'll have it. So the split plot, I think if I show you an example, it's sort of like a three-way factorial, but it has structure and it has multiple error terms. So I'll show you an example, and the book gives several other types of examples. And so for example, you could have schools, you could have teaching techniques, and then you could have time periods. There are a lot of ways that this arises in many different fields. But what I'd like to do is show you that this is the data we're going to be looking at. And I'm trying to find a picture. Oh no, the picture's not in here. That's right. This doesn't have a table of contents. It's going to take a kind of no good way to get there other than to scroll fast. Split plot, yeah. Okay. I've forgotten. Okay, this may help if you look at it from this sort of a visual way of looking at it. Not too crazy about the example, but does illustrate it. Suppose you have 6 carcasses, and this is with beef. And then you have 3 roasts that are cut from each carcass. And so under Roman numeral 1 are the 6 carcasses, and then the 3 roasts are the things that look sort of like a roast. And then you have 3 tenderizers. In other words, you're treating the carcass as a block. And if you forget the little circles and just look at the 3 roasts, then that would be a randomized complete block. You have 3 treatments, C, P, and V, and those represent 3 different tenderizers. Well, one's a control, one is a vinegar-based tenderizer, and the other one's a papain-based tenderizer. And so you randomize those on the 3 roasts. But then what you're going to do is those four circles are actually cores that you cut into the meat, and you're gonna put the roast in, and you're going to remember we have tenderizers. You're gonna put the roast in, and you're going to broil it or bake it, whatever, but broil it, I guess. And then after a certain period of time, you're going to take out the 1s, and then you're going to take out a certain time later the 2s, and then the 3s, and then the 4s. So that the time it's cooked varies from 1 to 4. I forget the exact amount of time in this particular experiment. Yeah, it's 30 minutes, 36, 42, and 48 minutes. So here's the data. So now this is sort of organized so that these are the 6 carcasses, and then these are all the controls for each of the 6 carcasses. Now, in reality, of course, the control is randomized. So here I have a control, here I have a control, here I have a... So it's randomized. But if you line them up, in terms of the way you look at the data, we put all the controls here for the 6 carcasses, all the vinegar-based and all the papain-based down below. And then we're going 30, 36, 42, and 48. So that's the data. So you could just say, well, isn't this kind of like a 3-way factorial? I have carcass, I have tenderizer, and I have time. Well, but it's a question of how you randomize the experimental units. I randomize the experimental units within each carcass. So that's like a block design. And then within each one of those, I randomize, for each roast, I randomize the 4 cores in terms of which one is 30 minutes, which one is 36, which one is 42 and 46. So I'm doing 2 levels of randomization. And so what we're going to do is we're going to call these carcasses sort of the whole plot, and we're going to have then subplots within it. So that's sort of the basic idea of the model. Now, what I'd like to do is sort of look at it now from the point of view of statistics, and this is the output. Now we have a file called beef.txt, and here's the .ormd file. And then, so when I ran this was just in a table, and it has the headers in it, so I just did a read.table. It creates a data frame. And saying head beef just prints out the first 6 observations of that data frame. Now you notice that time is going to be numeric. It's actually right justified, and so that's numeric as far as we know now. So we're going to make it into a factor because there are really just 4 levels of time. So we're going to make it into a factor. And then we're ready to run the model. Now we're going to run AOV, which is a wrapper for LM that will do an analysis of variance. But it does allow an error term to be specified. But there's one little problem with this. In other words, we get the correct answer, but it doesn't know we did. So I said tenderness is modeled as carcass. Now notice I have carcass plus tenderizer asterisk time. What does the asterisk do? It expands into a factorial. So that's really equivalent to tenderizer plus time plus tenderizer colon time. And then I have the error carcass colon tenderizer. Okay? So I was sort of playing around with some other things. This was actually, well, this ANOVA should be on another line. That's where the first statement ends, but I decided to run it this way. So what this really is carcass plus tenderizer plus time plus tenderizer by time. And then the error term is carcass by tenderizer. But there's actually another error term, and that's the remainder or residual. In other words, that doesn't find all the degrees of freedom we have. So there are 3 tenderizers and 4 times and 6 carcasses, right? So we get the following model. Forget that warning message about the error model is singular, because in fact it actually gets the correct thing. If you look down below, you notice it says error carcass by tenderizer in this one group, and then it says error within. That's the other group. So what's happening here is that we break, there's what's called a whole plot in the top, and the bottom part is what we call the subplot. And so in the top, we have the completely randomized design. We have carcass with 5. This is exactly, if you look at that top part, it's exactly like a completely randomized design. Carcass, there's 6, so there are 5 degrees of freedom. Tenderizer, there are 3, so there are 2 degrees of freedom. And the product of those 2 is 10. So I get those sums of squares associated with it, and I get the mean squared by dividing by the sum of squares, and then I get my f-test. And we notice that both carcass and tenderizer are very significant. Now we have the time, and the time by tenderizer interaction, and then the residuals. Now, how do we get, well, there are 4 times, so 4 minus 3 would be, 4 minus 1 would be 3, and tenderizer by time, okay, tenderizer has 2 degrees of freedom, time has 3, so 2 times 3 is 6. But where does the 45 come from? Well, notice that if you think of it as being the pooling of the interaction of carcass with both time and tenderizer by time. Now look at carcass, which has 5 degrees of freedom. Now if I multiply 5 times 3, I get 15, right? And if I multiply 5 times 6, I get 30. And if I add 15 to 30, I get 45. So that residual is really 2 interactions. It's really the interaction of carcass with time and carcass with tenderizer by time. Does that make sense? Look at the degrees of freedom. Again, carcass has 5 degrees of freedom, times 3 is 15, and then 5 times 6 is 30, and those 2 together give you that. So this residual you could think of as being the interaction It's the pooling of two terms, the tenderizer by time and the tenderizer of the carcass by time and the carcass by tenderizer by time. Okay? And that's our second error term. So when we say multi-level, what we mean is that there are two error terms. There are two levels. There's this whole plot level and then there's subplot level. So that's, and notice here that we also have significance. Now, what are you most interested in? You're most interested in the interaction. You want to know, you want to be able to look at the profiles of the tenderizers over time. And in fact, if we look at an interaction plot, which I've done down here, I just say interaction plot time by tenderizer. Tenderness is the response variable. It's kind of confusing because tenderizer is a factor. Tenderness is the y variable, the outcome variable. So that's the interaction plot. And so we can see as it turns out that as you cook more, it gets more tender. However, you probably know that if you cook too much, it will start getting too well done, and in that case, you could actually have the scores goes up. What it is, you cook it, and then they have this machine that cuts through the meat, and the lower the score, the lower the tenderness. I mean, the more the tenderness. Okay, if it cuts through more easily, it's more tender. Okay. So you can see if I'm looking from 30 to 36, I don't have any interaction there because the three lines are parallel. But what really seems to happen at 42, they sort of all come together with the same amount of tenderness. But then at 48, notice that two of them, the control and the vinegar, sort of level off, whereas the pepin keeps getting more tender. So again, there are certain consequences when you go into a restaurant and you ask for medium or rare or whatever. There are certain consequences, but again, this is assuming that a tenderizer is used, which it may not be, and it probably wouldn't be in a really good restaurant. Okay, so that's the interaction plot. You're typically interested in that. You can see that, you can tell that there's going to be a big time effect because it starts out high and by the time you end it's much lower. And we can see overall that there's a tenderizer effect, but that tenderizer effect's not uniform. In other words, the difference depends on the time. The difference between the three at 30 and 36 is about the same. But then the difference at 42 is sort of evaporated. The differences are the same at 30 and 32, but then they all come together at 42. So that's the cause of the interaction. Well, let's back up a minute and let me make this a bit bigger. Maybe that's too big. Let's look at the model. What we're going to have is mu plus gamma sub k plus alpha sub I plus delta sub ik. Those three terms make up the whole plot. They are a randomized block design. Okay. So in other words, gamma sub k is the k block effect, and blocks are random. And then alpha sub I is the effect of the ith level of the factor A, which is the whole plot treatment. And delta sub ik is the whole plot random component. And we're going to assume that random component is independently normal, for mean of 0 and variance of sigma squared sub d. Now you could argue that that random component is really the interaction. If gamma corresponds to C, it's the interaction between C and A, you could argue. Because the degrees, look at the degrees of freedom. So I look at the 10 here. Where do you think you get that? Well, that's just 5 times 2. And I mentioned this before, that error term is really confounded with the interaction. So if there really is an interaction, and this is the same thing with a block design, then it's going to inflate that error term. Because that error term will be the whole plot residual variability. And if there's interaction in there, then it could be bigger. And then if it's bigger, that means that the power for, if by bigger I mean the sum of squares is bigger or the mean square is bigger. So that would imply that the power is less because the denominator of the test will be bigger than what it should be compared to the situation where there is no interaction. So at any rate, that's the whole plot analysis on top. And we have our f-test. And now we start this last part of the model. Beta sub j is the subplot, or what's called the split plot treatment. Let's go down here. So in our case, that's the cooking times in this example. And the alpha beta is the interaction between the ith level of A, which in our case is a tenderizer, and B, which is time. So that alpha beta ij is the interaction that we're most interested in. Now, if there is no interaction, in other words, if alpha beta ij, if we don't even come close to rejecting it, so we say, okay, there's no interaction, then attention drops back to the main effects. But it's hard to interpret the main effects by themselves if, in fact, the interaction is significant. And then we have the split plot random component. So that's the model. Now, as I said, we are assuming that alpha gamma ik equals 0 for all I and k. If not, this interaction is confounded with the whole plot random component. I said that before. It's something you have to be careful about. And likewise, we're assuming, and again, this is this other error term, likewise, we're assuming that beta gamma jk equals 0, and alpha beta gamma ijk is 0 for all ijk, ij, and k. If not, these interactions are confounded with the split plot random component. Okay. And that was what I was trying to show you. Now, here are the expected mean squares. And again, these follow the same rules. The only difference is that where I have a d, you could really think of that as being the AC interaction. I mean, where did you get the 4 in front? The 4 sigma squared sub d. Well, 4 corresponds to the 4 times, and that's the B effect. Well, what's in the subscript? Okay, you see a D, but what is D? What I said is that D is really the AC interaction. That is, it's the carcass, in this case by tenderizer. Carcass is the C, and tenderizer is the A. So it's really the AC interaction. So what's out in front is what's not in the subscript, which is the 4 for the 4 times. In other words, that represents the 4 levels of time, which is not in the subscript. So that's why it sort of seems strange in terms of, well, where did we get the 4? But you have to kind of sort of pretend like, well, okay, this is really like, the AC interaction. So what we get, notice for the whole plot, all of them have sigma squared plus 4 sigma squared sub d. And so the carcass, is a random component. So it's sigma squared sub c. And then tenderizer is a fixed effect, so it's the sum of the alpha sub I squares over 2, actually, and then which is a minus 1. And then what's in front is 24, which is the b times c, which is 4 times 6, or 24. So you can see that the error A, which is the whole plot error, tests both carcass and tenderizer. And now we go down to the subplot or the split plot, and we see that for time, it's 18, the sum of the beta sub j squared over 3. And then we have the tenderizer by time, which is the alpha beta. Now the time and the tenderizer are both fixed, whereas the carcass is random. So you can see that we'll use the error B to test those two terms. So that's what this analysis did up here. Now these may differ from the book because the book rounds off. In other words, if you do your arithmetic and you round it off, and then I divide these means, if I round off the mean squares, and then I divide, to get the f-test, and you've rounded off a lot, you can get very different f-tests than what you would get if you kept the precision. So I forget what the book has, but I think they're somewhat different. But this is correct, because this is holding the precision. So that 0.05 may not really be 0.05. That's just the print representation. It might be 0.05 something. Because if I would divide 10.36 by 0.05, it would be over 200, right? But it's less than 200, and that implies that this has been, internally the precision is kept. It's just not printed, but internally it's there. But if you would just divide 10.36 by 0.05, you wouldn't get 190. That's because it's really something like 0.053 or something like that. So it's not surprising we have a time effect, but as I said, the key thing is you're interested in that tenderizer by time. Now you could argue that papain always seems to be the lowest. And the only time you would, if you wanted tenderness, then it's always the lowest, except that when it's 42, they're all about the same. But if you were just going to go with 1, that would be the 1. So there's our model, and we computed the expected mean squares, and then we can get the f-test. And here are the critical values, and we can see that, by the way, you could, let's see. Technically you could test error A by error B. In other words, error A is sigma squared plus 4 sigma squared sub D, and error B is, that 45 is the degrees of freedom, that's not a coefficient for sigma squared. So the sigma squared, error A could test error B, but that's of some use because that tells you there's a lot of carcass variability. There is some reason you may want to do that. Of course, really the carcass variability is sigma squared sub C. This is more like as I said, more like an interaction effect. So if you wanted to get a variance component, you could do that. Okay. Now we can also do multiple comparisons, and it turns out that they're fairly straightforward, except if we're looking at the interactions, what might we want to do? Well, the thing that you'd probably want to do is compare the treatments at a certain time. So I want to compare those three treatments at 36 and 42, etc. I'd like to compare the treatments at each given time. So here I could compare them, here I could compare them, here I could compare them, and here. But it turns out that if you do that, if you compare the same A level, if you compare the A levels at the same B level, so it's like comparing the treatments at 30 or 36. So if I compare the A levels at the same B level, it turns out that the error term is not as straightforward as you might think. The error term, and right here we're seeing y bar sub I j dot minus y bar sub I prime j dot. That means I is different. So at any rate, what I have done here below is I've calculated the means right here. What I'm doing is calculating the mean. I'm making a list, and I'm calculating the mean over the mean of tenderizing in time. And so these are the means, and again I'd be comparing within each of these at different times. And if I did that, it's like a Fisher's OSD, except that there's no single mean square I use as an error term. I have to use, there are two of them. The first one is MS, and the subscript is SR. This first one has a subscript of SR, and that's like the subplot or the split plot, and then the MSWR is like the whole plot. So it's 2 times B minus 1 MS sub SR, that's the subplot error, plus the mean squared of WR, which is the whole plot error. The whole thing divided by CD. C is the number of carcasses in our case, and B will be the number of times. But how do I get my t-value? Well, you see, this is like, remember when we talked about an F synthesis, where we have to synthesize the F test because we don't have, when we compute the expected mean squares, we can't get them to line up exactly, and so I have to combine mean squares, and that means we have to compute this kind of wild, the question is then, okay, I can do the F test, but then I have to get degrees of freedom in order to do this. Well, this is how you can compute the t-value in this case, and again, it's a weighted average of these mean squares, weighted by B minus 1 and 1. And so this involves both the whole plot and subplot errors in order to test this. And this is probably what you're most interested in doing. It's comparing the A's at the same level of B's. Now, I actually, so we could do that. I didn't actually calculate that out, but we could do it. And we could do all the comparisons. In other words, once we compute this, then we can compare all these differences for the different values of J. And do it. We get quite a few, though, because, for each column, you're going to have 3 comparisons. You're going to have control of the pain, control of the vinegar, and pain to vinegar. You're going to have those 3 comparisons for each of the 4 columns, so you're going to have 3 times 4 comparisons. So you get into this problem of multiple comparisons we talked about before, and what should be should we be adjusting the p-values so that we protect ourselves a little bit more than straight doing a Fisher's LSD? And the answer is probably yes. And so, if I continue down, there's one other thing I did here. And what you really have is a control, and then you have two tenderizers. So suppose you want to make two contrasts. One is the control versus the two tenderizers, and then the next one is the tenderizer versus the other. So what I have down here is I have the control versus P plus V. Okay, and the control, of course, is the control, and then P is propane, and then V is the vinegar. And then I have P versus V. Now, what I'm saying is that the two contrasts are 2, -1, -1, and then 0, 1, and -1. If I take the inner product of that, what is it? It's 0. So therefore, we have orthogonal contrast. We have orthogonal contrast to do this. Now, it turns out that what I'm showing you here, and this is a little bit technical, but what I'm showing you here is I'm binding together these two contrasts, and then I multiply the contrast times the tenderness and get the sum for the contrast, and I square the sum and divide by 24 times the vector of 6 times 2. 6 comes from 2 squared plus 1 squared plus 1 squared. That's the sum of squares of these coefficients is 6. The sum of squares of these coefficients is 2. So this vector gives the sum of squares of the coefficients. So that's sum of the c-sub squares. And then the 24 is the 4 times 6. So that actually computes this is really a vector of, this is really, there are two values. Since I have a vector since I have the 6 and 2, I have a vector there. I actually, the sum of squares for the contrast is actually a vector also. And so what I did is I took those sum of squares, and I took the sum of, I have the sum, in this, what I'm doing is getting the sum of squares here, and then I'm taking the sum of squares and dividing by the error term to get the mean squares, and then I'm getting the critical F values. Oh, let's see. Oh no, I see. Yeah. This is, I'm sorry. This in fact, what I call the sum of squares is really the mean square. Why? Because each one of those has 1 degree of freedom. So if I divide the sum of squares by 1, I get the mean square. So in other words, in this case, the sum of squares equals the mean squares. Is that clear? So I wrote this. I said SS divided by 1 equals mean square. So this column is the mean square. It's also the sum of squares. So it corresponds to this first column. Then when I take the mean square divided by this 0.0545, and that 0.0545, where did it come from? Well, it is really this value right here. And that is rounded off to 0.05, but it's really 0.0545. So that gives me an F-test. And then these are the critical values. And you can see they're both highly significant. Now I want you to notice something. We have 2 degrees of freedom here. Now I want you to add up the sum of squares. What is it? It's about what? 14.694 plus 6.021. So that is about 20.7, right? Well, it turns out that the sum of those two is equal to that. What we did is we have orthogonal. We took tenderizer and we broke it into 2 pieces, each with 1 degree of freedom. 1 plus 1 equals 2. We had that as 2 degrees of freedom. We broke that treatment tenderizer into 2 single degree of freedoms, and they're orthogonal, so they add up to the sum of squares for the tenderizer. So I'm just breaking it out. Now, what you might also want to do is take time, and there's a concept of orthogonal polynomials. Orthogonal polynomials try to take time, and they fit a linear effect, but they're orthogonal. And so you have a linear effect, then you have a quadratic effect. In this case, we have 3 degrees of freedom, so we could fit a linear, a quadratic, and a cubic. And the coefficients are determined in such a way that the first one, for the linear effect, we get coefficients that represent it, and we get a quadratic effect that's orthogonal to that linear effect, and a cubic that's orthogonal to both of them. So we could actually break the 3 degrees of freedom of time into 3 orthogonal contrasts that correspond to what we call orthogonal polynomials. And we could do that. Because it might be that the linear effect is significant, but not the quadratic or the cubic. And then, of course, we could, technically, that's 6 degrees of freedom if you took the 3 contrasts below and the 2 above, and 2 times 3 again is 6. But that's probably not what you'd want to look at. Probably, as I said, what you probably want to look at are these pairwise comparisons of looking at the A levels within each B level. Okay, so that's the gist of what we're doing here. Any questions? Well, let me show you this in JUMP. So in order to do that, I need to go into the server. So here's the data in JUMP format. And you can see that there are 72 observations. Three times 4 times 6. Okay. So how do we build the corresponding model? Well, I go analyze and I say fit model. And of course, tenderizer is my outcome variable. I had already changed, originally time, originally when I had time here, originally time wasn't justified to the left, it was justified to the right because it was considered numeric. And what I did is I went in and I went in here and originally it was numeric and I changed it to character. Now, you could technically change it to character nominal, ordinal, because it is on an ordinal scale, going from 30 to 36 to 42 to 48. So that's really an ordinal scale. So we could have done this as an ordinal. And in fact, if you did that, then by default, R uses orthogonal polynomials. But I'm not in R. So going back again, if I say fit model, and we have tenderness, and so what I want to do is I'm sort of going to add these in the order that I want them, and so I'm going to add that, and then what I really have now is the carcass. Let's see, carcass by tenderizer. I have to select those two, and then I say cross. So I have carcass tenderizer, tenderizer by carcass, or carcass by tenderizer, it doesn't matter. And then I have time, and then I have tenderizer by time, so we'll select both of those, and we'll cross those. And then that's all I'm going to do. The final term I'm just going to leave out, which means it will be the residual. Is that clear? So I just leave that out. But I'm not finished yet because I need to make carcass. I need to make it a random effect. And I need anything that has carcass in it a random effect. So the tenderizer by carpet is also a random effect. And then I'm going to actually go back and do the traditional method. And let's keep this up here. And I'm going to well, initially I'm going to just print out the minimal report. I'll come back and redo it in a minute. Now, what you get is these are the coefficients that give you the expected mean squares. So those are the coefficients for the different terms. That's a not so nice way of looking. In other words, when I have tenderizer, its coefficient is 24. And I also have a tenderizer by time interaction that has a coefficient of 6, and then a carcass which is random. Now, if you go back and look at what we did, that's the carcass by tenderizer here. So that's the, it's got tenderizer by time. Okay. Oh, yeah. Yeah, this is, of course, the tenderizer by carcass is, we have this term, and we have this term, but it's also picking up the tenderizer by time, which we don't. And so you might ask, well, let's go down and look at the, oh, wait a minute. Did I set that model up right? Yeah, I did. Tenderizer by carcass. Carcass tenderizer, yeah. Okay. I'm a little puzzled. It says here that tenderizer is, the denominator synthesis is tenderizer by carcass. Okay. And that corresponds to this term, but it doesn't count for the fact that there's also this term. So I'm not quite sure how they came up with that. I'm missing something? Let's look at carcass a minute. Yeah, see, carcass says this, carcass which is random, and then these line up. So clearly the tenderizer by carcass is correct for testing the carcass. But since the tenderizer put in this extra 6, and that's because it uses this alternative model, which we didn't put in ours. It almost seems to me like you have to combine the tenderizer by time with the tenderizer by carcass, because the tenderizer by time picks up the 6, and the tenderizer by time picks up the 6, which cancels out that 6, and then this 4 cancels out that 4, and it only leaves this. So it seems like, to me, it would be There's some of those too. It's a little puzzling. Because that's not what it says it's doing. Am I missing something? I don't think so. Anyway, I may have to explore this a little bit more. Because the way we tested it using the standard model is we would, of course, use the carcass by tenderizer as the error term for tenderizer and carcass, but we're mainly interested in the tenderizer. Now, in terms of the time and tenderizer by time, that are residuals, and that's fine. We're the same there. Okay, so I got to leave that kind of up in a question. Any questions on this, other than the fact that it doesn't appear they're using the right error term? Okay, so that's how you would do this in JUMP. I did want to show you one more thing, that if you wanted to get the interaction plot in JUMP, then you have to do the full report. And if we do effect leverage and I rerun it, you get this big table. And if I go over here to where it says tenderizer by time, I can go down and I can look at, I can look at least squares means. But see, that just compares everything to everything. And so that's not really what you want. Whoops. Whole plot. On the other hand, if I go down and do the plot, you recognize that? That's the same plot that we had before, right? So that's the interaction plot using the least squares means. Unfortunately, I don't think there's any easy way to get the multiple comparisons from JUMP. As I said, that you don't get it from here. You could do your own contrast here. So you could, this looks at control 30, 36, 42, and 48 per paint. In other words, there are 12 of those. And you could do your contrast like with the 30, 30, and 30. You could do the contrast within those. So if I wanted to control versus propane and vinegar, then I have 1 minus 1 minus a half minus a half. And those coefficients, if I would do that, I would be doing the comparison of the control to the propane and vinegar within the 30 time. If you think of it as a plot, I would be looking at that contrast within this. And then if I did a second contrast, let's see. It's not what I meant to do. Yeah. I would have to do a new column. And then I could do plus, minus. And so these two contrast together. those two contrasts together would give me the overall contrast I did, where I did control versus the other two, and then each of the two, except that's only within time 30. You see what I'm saying? So I could do that same orthogonal contrast within this, and so forth. Or I could simply do multiple comparisons. So now that I've erased it, I guess I have to go back. Yeah. I mean, I could do 1 minus 1, 1 minus 1, and then 1 minus 1. Now, well, actually, it's not doing it. It's not actually going to give you. It's not going to actually give that to you because it forces you. You can't have more contrast than you have degrees of freedom using this software, it appears. So you can't do the pairwise comparisons the way you'd like to do it here, that I can see. Okay, any questions? Okay, so let me go back then and look just briefly. We'll have to finish next time, but I'm going to go into into 7, which is the last section here. So I'm going to go in and take a look at this. And so I'm going to look at these models, and I'll show you how they differ. This is truly hierarchical in the following sense. If you look at this example, by the way, in the book, this is where they're talking about comparing means, comparing the attendance means at the same Racine time. We have another example here, and this what are they using over there? I've lost it. Okay, that's that. I'm looking for section 7. Okay, this is it. Split plot with repeated measures. Now the main difference here is conceptually, if you look at it, you have groups and you have subjects within groups, and then you have determinations at different times. So the top part is a completely randomized design. So in this case, what we have is a completely randomized design in the whole plots, and then we have these subplots that are measured over time. Or we can think of them as subplots, but what it really is measured over time. But it's actually a little more general than that because it could be measured over space or different ways we can conceptualize this. So what we've really kind of done here is we've taken the previous design and that whole plot, instead of being a randomized complete block design, it's a completely randomized design, like a one-way analysis of variance. So that's the main difference. It's fairly simple. Now, next time, the order of the chapters becomes important because, as I said, the analysis of variance two-way and three-way should probably be put back with Chapter 11, which is the one-way analysis of variance, and that talks about mixed models and all that stuff. And then you go into the two-way and three-way. And what's the next chapter you should have is the next chapter we'll cover, which is called the analysis of covariance. Because what analysis of covariance allows you to do is to measure continuous variables along with your categorical variables that you have in the analysis of variance. So why could that be, important? Well, we could have covariates at either the top level or the bottom level or both. In other words, on the subjects, I could measure covariates, but I could also measure covariates at the subplot level. So, for example, if the treatments, if the subjects are actually people, and the groups are actually treatment types, and then I make measurements over time to see if there's a change, then if I have covariates measured on the patient, for example, their weight, things like that, those would be covariates that would be measured on the whole plot, or in this case, the subjects. But if you measure it at different times, you could also measure covariates that are different from time to time. So that's why you probably should teach the analysis of covariance before you teach this, because in these multi-level models, they may or may not have covariates. Often they do. Just keep that in mind. So what are we doing? We're going to look at an experiment. And this has to do with the effect of E. coli. E. coli generates this chemical, LPS, and if it becomes prevalent in your body, it causes, I think it's a heart, is it a speed up or a drop? I think it's a speed up of your heart. It causes your heart to race. And so, if you look at that and then you compare it to a control, which doesn't, then you're asking the question, is the LPS causing a speed up of the heart, and does that speed up drop off over time? You follow what I'm saying? We're going to do this on rats, not people. So you inject the rats with E. coli. The animal rights people after us now. You inject the rats with E. coli. That's going to speed the heart up, but then you measure with time to see if it drops off. But you're also looking is the LPS in general, is it higher than the control rats, which don't get any? They have a placebo. They're not getting. They either have another compound or it's a placebo, which it could be another compound that also speeds the heart up, depending on what your research study is about. So here's the data. You have treatment. I think there are just two treatments, LPS and control. And then we have rats. Now, rats are nested within treatment. So, and then you measure at 0, 20, 40, and 60 minutes after the injection. Okay. So I think there are, just 3 rats? There are 2 treatments, 3 rats. And then there are 4 times 0, 20, 40, and 60. So does everyone understand the experiment? This experiment is very common. Again, if you think of it's hierarchical, there are 2 error terms. And so I have heart rate, H rate is heart rate, tilde treatment times time. So that's a two-way factorial. And then I have treatment time and treatment by time. But the error I'm going to break out separately besides the residual is the treatment by rat. Okay, now what that's going to do is break this up, and I'm going to have treatment of 1 degree of freedom. Remember, there are only 2 treatments, so A minus 1 is 1. And then I'm nesting rats within treatment. And so you're going to have A2 times B minus 1, or the number of rats minus 1. And if 3 rats, it'll be 2 times 2 or 4. And so we get our F-test. It's not, the treatment effect is not significant. However, when I'm looking at it over time now. And so when I look at it over time, which is the subplot or the split plot, I have time and treatment by time. And there are 4 times, so that's 3 degrees of freedom. Treatment has 1 degree of freedom, so 1 times 3 is also 3. So I have 3 degrees of freedom for time and treatment by time. And you notice both of those F are highly significant. And the error term has 12 degrees of freedom. So I'm hoping I have the there's the interaction plot. So that's highly significant. So you can see from 20 to 40 there's a crossing effect. It appears that the control, and that may again just do the randomization. In other words, there's no reason at time 0. It should just be random which one is highest. Do you follow what I'm saying? You haven't, depending on how they define time 0, because there's always a before and after. If they inject it and immediately measure, but ideally you'd probably measure and then immediately inject. And you notice that the control drops off very, very quickly. I'm not sure why it was high. Maybe it was another compound. I forget what they said. Maybe it was another compound. Because you would think the control would be kind of level, horizontal. I mean, there's no reason why, if it really is a placebo, unless the blood pressure is going up because of anxiety, there's no reason you would expect it to change over time if it's a placebo. At any rate, you can see where the interaction is. From 20 to 40 to 60, there's no interaction because it's parallel. It's really in that first 20 minutes is where you see the interaction. The control drops off much more quickly than the LPS. So that's why we're getting the significance. And notice you would think that the treatment would be, certainly if you were just looking at the last part, there would be a treatment effect. But here we have this crossing effect where they cross each other. So they tend to cancel each other out, at least between 0 and 20. And that's probably destroying the treatment effect. The time, of course, is highly interactive. I mean, they're both going down. So from the top, the upper left to the lower right, there's a drop-off. Well, let's see. Yeah. I'll spend a little bit more time on that. I just wanted to show you. Let me just mention that here's the model. It's mu plus alpha sub I plus beta sub ij. I'm sorry. Yeah. This beta sub ij is the error term that's the error term for the whole plot. Notice it's an ij. There's no interaction alpha beta. There is no alpha beta ij. There's just a beta ij. So what I'm saying is that the j is nested within the I. That is, we have a nested design of rats within the groups or within the 2 treatments. And so we have beta ij, and then we have plus gamma sub k, which is time, and then we have treatment by time. And then we have the second error term. And just for reference, here are the expected mean squares, and you can see that this b right here, you can really think of that b as you might wonder, well, why is that a B here if there's a B down here? It's because the B is not really quite a B. It's more like an interaction. So at any rate, this is a nested design, and we can look at the expected mean squares for that. I mean, if you only had the nesting. So at any rate, these are the expected mean squares, and you can see that both of the factor C and the AC are going to be tested by the residual, and the factor A would be the within experimental units within A would be testing it. And so that's what we did up here. So I will come back and talk. There's a little bit more about this, and then I will go and do the same thing in JUMP that I did before. I need to reconcile what JUMP did with those coefficients. And what we're going to do now is, after this, is next time we'll also start on chapter 13. I'm going to go ahead, I'm going to, as quickly as I can the next day or so, I'm going to post the assignment for chapter 12. I think what I'm going to do is just have an assignment for 12, 13, and 14. And that adds up to 175 points, and I'm just going to give you the other 25. So I'm just going to have one assignment for chapter 12, one for 13, one for 14. That adds up to 175. So you just get the other 20. Okay? So I'll post, I won't have time tonight, but I'll post this hopefully on Friday for chapter 12.